Okay, so sorry. So this is the first problem, right? So there's problem section. So the one on the left, the circled product, that's favored with methoxide as the base, because it gives the more stable product, the Zaitsev product, follows Zaitsev's rule, and the more substituted one. The one on the right is favored with terbutoxide because it forms the less sterically hindered alkene. Okay?
Is oxide OH or just O?
Yeah, let me show you. Terbutoxide. Okay, I will show you how so these are reagents you should know. Thank you very much. So I'm going to rewrite it a little bit so it's a little bit clearer. So essentially what I'm going to do is I'm just going to take off this one and then write it as a separate. Okay? So we're going to say with methoxide, that's OMe minus. All right, that's methoxide. You're forming mostly this product. This is the Zaitsev product. Okay, the more substituted alkene. Now with tertiary butoxide, it looks like this. That's tertiary butoxide. With tertiary butoxide, you form the less substituted alkene. This one. Sorry, this I'll do like this. Okay, and so this would be called. How is it called? A Hoffman product. Hoffman. I don't know if it's two F's or one F. One F. Okay. Hoffman product. All right. Next question. Starting off easy. They're gonna get harder. Okay. Oh, sorry. You want to see it again? That was a little bit too fast. All right. Are you guys good? Go to the next one. Okay. Here we go. Same question. What do we form with methoxide in an E2 reaction, and what do we form with T-butoxide, again with a sterically hindered base in an E2 reaction? Who wants to try to draw the products? Caroline. All right. Here we go. So normally, the Wednesday night review sessions, if you haven't come yet, we still wanted to come. I usually give out apples if you do a problem. Okay? This is even more agreeable.
So isn't there only one? Or with resonance, are there more?
There's only one product.
Okay.
That's a trick question. You form the same product with T-butoxide and methoxide because there's only one beta hydrogen.
Yeah.
Right? That's a trick question. I mean, not a trick question, but
That's what yeah. Okay, good.
All right, great. Thank you. So there's only one possible product which can form. That's this one. All right. So let's go to the next one. Give you another 10 seconds to draw it. All right, are you guys good? Okay, let's go to the next one. This one. What do we form? With, again, methoxide. I'll put the methoxide. So here there's two products now, right? Because you see, again, there's a beta hydrogen here. There are two beta hydrogens here, all right? So with methoxide and with T-butoxide, what do we form? Let's get somebody else. Is anybody willing from the back to give it a shot? Yeah. You're not in the back. Look in the middle. Let's still give it a shot. Thank you. Oh.
Okay. So with methoxide, we're gonna form.
No, that's fine. So again, with methoxide, we form the more substituted, the so-called Zaitsev product, right? So I'll turn the mic down a little bit.
Do you want me to do both of them, or?
Yeah.
Okay.
Say again?
Never mind.
I'm coming. All right. Sorry. Did you have a question?
I was just asking if I was supposed to draw both or not. But
In this case, just draw the major one with each. So you form a little bit of each, you form a little bit of the minor product for each of the cases. All right, so that's great. That's fine. So we'll say, thank you. So I will say, so for example, on an exam, I would say something like this. I'll say what products that may be called major only. You know what I mean? Then you just have to draw the major one. Usually if I'm But you're right. Actually, both of these products form, right, with both bases. So sapling usually asks for both of them.
Yep.
All right, or on the exam, depending. If I want you to draw both products on the exam, I will say draw both the major and minor products if there's multiple products. That makes sense. I'll try to be clear. So you have to be really, really careful about reading exactly what I'm asking for. A typical thing to do would be draw all the products for the following reaction, right, and circle the major one. Does it make sense? So then don't forget to circle, because that'll give you points for circling and stuff like that. All right? So, next one. You guys good at this side step stuff? Yeah. Okay? Now here, what starting alkyl halides would you, let's say you want to make a mixture of these two guys, what starting alkyl halide would you use with an E2 reaction? Who wants to give it a try? It's like the reverse. You see, that's the reverse kind of problem. See, Isaac will give it a try. All right. So I don't have a super great handle on time yet. I don't know how long it's going to take us to do the problem. We'll try to go pretty quickly. If we have extra time at the end, you guys just ask a couple questions, okay? But what happened in the review session is we spent like half an hour to do the first couple problems. So this is great. This is perfect. Okay. So why this one? Why not, for example, why not, let's say, this one? Why not this one?
So if you have it on the one that you drew, if you have the halide on the one that you drew, you won't be able to get the
one on the right.
The ketone
Yeah, you
on
see.
the right.
So the one Isaac drew is the only one which has beta hydrogens in both positions where we want to eliminate, right? See, that one has beta hydrogens here. So this is not correct, okay? So you see the one Isaac drew has beta hydrogens there and here. And so that if you take one of the red hydrogens, of the yellow ones, you get this yellow product. If you deprotonate one this methyl group, and you see you have another methyl group, they're equivalent, then you get this product. Does it make sense? So that's why. So you have to be careful. You can't just put it at any position. You have to put it in the right position so it gives you both products. So let's go to the next one, okay? This one. Thoughts? We want to form only this product, nothing else. How can you do it? What alkyl halide are we going to use? Don't want to form anything else, right? We don't want to form a mixture of stuff. Try. So collectively, we are still pretty good at doing these problems. See? Maybe we can do the exam in a new way, like somebody's group exam, you just hand it around. To like 10 exams, split up the class into like 5 groups and you hand it around, everybody does the problem they can solve.
This is not very pretty, but...
No, that's perfect. That's absolutely perfect, all right? And again, why this one? Because you see, this is actually a cool problem. This has symmetry involved. Thank you. It's the same thing. You see this one? So you do it like this. Look, there's these hydrogens here. Regardless of which one of these 4 hydrogens you take off, you're going to get the exact same product. You see that? Because it's just, if you take the one on the bottom, obviously you get this one. If you take the one on the top, you get this one. Right? But that's the same thing. That's just, you just rotate it around this axis. Okay? Then it's the same thing. You guys see that? It's not a hard problem, but it requires some thinking. That's a good problem. Any questions? A couple questions here. Let's see. Who was... Did you? Oh, no. Oh, you. Okay. You guys had questions.
So I feel like the second you draw it, it'll be clear. But why doesn't it work on that bottom, like those 2 H's?
Yeah.
Like
Let's draw it there.
Yeah.
the best thing to do is you try it out maybe 2 different ways on scratch paper, and then that's how I would do it. I do it in my head like this, but you can write it on scratch paper, you know what I mean? And then you try out both ways, okay? So yeah, the other way, you see, essentially when you have the double bond, right, here, and I'm asking a question like this, you have to basically put either the alkyl halide on this carbon or on the other carbon. But one of the carbons has to have the halide, and the other carbon then has to have the hydrogen. Those are the 2 possibilities. So I just drew you one of them where we put the halide on this carbon. Now the other possibility, what Caroline is mentioning, you could put it on, you could take a starting material where the halide is here. For example, let's put X, right, because you guys are putting X. Let's do it here. Now if you do an E2 reaction, say again, Isaac? So if you're taking this, you're doing an E2 reaction with, for example, T-butoxide, you're gonna get mostly this. Okay, you're gonna get major this product plus minor. The minor product will look like this. You get a little bit of the Zaitsev product. Okay, that's not. So you see, major minor, that may be 90%. Of course, the more hindered the base, the more of the major product you get. You might get like 90% of the major product and 10% of the minor one, but you still have to separate out the minor product, which can be really hard, because they will run very similar on chromatography. You need like something like GC, gas chromatography, right, what you used in lab to separate them. And that only then, and even there, they are pretty close together. Now, how much did you inject in your GC? You can't just take like a whole test tube of material, pure material, and inject it. You take a solution, you inject like 10 microliters. So to separate this, get it pure, if you get a mixture, is really hard. Super, super hard, actually. I wouldn't know how to do it, frankly. Okay, because you can distill it, but it's like a pain. You have to do a distillation. So that's why it's much better to do this method, where you start from the symmetric, alkyl halide. You eliminate, you get only one product possible. So it's actually a specific reaction. The other one there, if you start with the alkyl halide on the bottom, is a regioselective reaction. So you can get 2 possible regioisomers. One is the major, one is the minor. You can adjust it by what base you're using, but it's not as good as just getting a reaction where you can only form one thing. Does it make sense? Good question. All right. So the one we want to use, this wouldn't be, I would still give points for this on an exam. Maybe not the full amount of points. Okay? All right. Let's move on. Same deal. How would you do it? What would we use to synthesize this? Same deal. We want to only make this product, nothing else. You want to try? So we can. Oh, you have an iPad. Oh, this is not an iPad. Let's see. Perfect. That's it, exactly. Because then you only have one beta. You only have one beta hydrogen, right here. Okay, only one, and there's only this one can be taken off. That gives you the product. The other option would be to do it like this, where you put the halogen on the carbon, on the tertiary carbon, but then it's not great because then you have beta hydrogens you can take off down here and up here, so that's not good. Okay, make sense? So let's move on. Let's see. Okay, this is a simple question. Do T-butoxide and LDA follow Zaitsev's rule? Explain when you do an elimination. You can just say it. I will write it. So we just raise your hand. Who thinks these follow Zaitsev's rule? Who thinks they don't? Okay, good. So they don't follow Zaitsev's rule, right? They follow Hoffman's rule. So we'll say no. These bases are sterically hindered and they follow Hoffman's rule, okay? As we discussed. And we just did a bunch of examples for that. Make sense? That's very important, to be able to distinguish which alkene forms. There'll certainly be questions on this on the exam, right? Now let's see the next thing. Now this is interesting. Okay, this is like how about biochemistry will look like. Have you taken biochemistry yet? So this is a typical reaction, right? So this will be more of a challenging problem, all right? But I'm giving you the starting material, the base, the product, okay? I'm telling you it is, so what happens? If there's a base there, it's probably an E2 reaction, right? And you see it form a double bond. You see it's an elimination reaction, but instead of using an alkyl halide, we are using a biological thing, okay? Because alkyl halides, biology can't make alkyl halides very well. So it uses things like arginine instead as the leaving group, okay? That's part of the question. So you want to try to draw the...
Yeah.
Okay.
Sure. Also, I have kind of a quick question first. In this instance, do we have to worry about the hydrogens being in line? Oh, no, wait. Are they already in line? I'm not sure. Is that something we should worry about for this?
Okay, your question is whether you have to worry about the anti-periplanar arrangement. And we'll go back to that after we draw the mechanism. Okay. So let's draw, number one, let's draw the mechanism, the arrow pushing. Okay? We draw the mechanism, and then we will figure out whether we have to worry about the anti-periplanar thing. The answer is in this case no, but I will explain to you
Excellent.
why. Otherwise it will be too hard. Okay, so this is the base. Yes, you take off a proton.
So then that goes to the double bond, and then this one goes to...
Sorry, that's just... If you push it too long, it will like a circle.
Yeah.
That's it.
I think so, yeah.
So, that's pretty good, except, you see, it's pretty much almost perfectly correct, okay? Except that, you see the way you drew your arrows.
Oh, it would lead to a different
It would lead to a bonding. You see, this carbon would have 5 bonds. Do you see that?
Mm-hmm.
And the carbon here you would still have a double bond. But you see, the product has only a single bond here and a double bond here.
Move like when it's a double bond to an oxygen?
Yes, you need to move that up.
Okay.
So try that. You just need to add another arrow.
Yeah.
Does it make sense? Yes.
Yeah.
But
So
if
just
you,
like when you have it with a double bond and an oxygen.
Same deal with when you do it with an oxygen. If you don't draw that arrow, that last arrow, you see you violate the octet rule on this carbon here. You see that? This beautiful green carbon there. You violate the octet rule. You make 5 bonds to it temporarily when you push the arrows, which is really bad. That's like one of the cardinal rules, okay? So otherwise it's absolutely correct. This is what happens, you see? It's essentially an E2 elimination mechanism. And so what is the role of arginine? Nucleophile base substrate leaving group. The leaving group, that's what gets kicked out. Normally, in a normal alkyl halide, this would just be the alkyl halide. This whole piece there is kind of like this is like the alkyl halide. This is the leaving group, this whole thing. This is the leaving group. Okay, I would say takes the role of an alkyl halide. Okay? And so it's the leaving group, that's correct. All right, so now thank you, that was great. So now to your second question, right? Or to your question. Do we need to worry about anti-periplanar arrangements here? That's right, because it's not E or Z, we don't actually have to worry about it. No, it could be E or Z, you're right. No, you're right. It could be E or Z, you're right. This product, this fumarate product, right? It could be the E fumarate or the Z fumarate, absolutely. Yeah, you're right. You were not right the first time, but the second time. So it can be E or Z, so but we still don't have to, so we form selectively the E product, right? Why? Because you see we have 2 hydrogens which can be taken off, this one or this one. And then we have 2 beta hydrogens which can be taken off. Either one of them can be anti-periplanar, right, to the leaving group. And so, I mean, you will have to rotate the conformation a bit, right? You have to rotate it. But either one of these 2 orange hydrogens can be anti-periplanar when you rotate. And you just rotate differently. And then means if you take off one of them, then we'll give you the Z product. If you take the other one off, then we'll give you the E product. So why do we selectively form the E product? Zaitsev's rule. Remember, we said that if you have 2 beta hydrogens you can take off, you take off the one which gives you the more stable product preferentially. So the actual situation here is that you form the fumarate, and this is the major product because there are 2 beta hydrogens, right, beta H's, which can be anti-periplanar. And this is so the more stable, oops, this should go somewhere over here, the more stable alkene forms, okay? Preferentially. That means preferentially. So the Z product is the minor one. The Z equals minor, okay? Sorry guys, can you read this? This is a little small, but make sense? Okay? Next one. Otherwise people run out of time. I want to try to get through all of these problems. So I think we have to accelerate, otherwise you're not going to get through all of them. All right? But these are a little bit easier again, okay? So that was a challenge problem, I think. Now, provide the missing products of the following reactions, okay? So here it could be either SN1, SN2, E1 or E2, all right? First thing you have to figure out is what kind of mechanism do we have? And what are the reagents? So LDA looks like this. It's lithium, LDA stands for lithium diisopropyl amide. So amide here doesn't mean it's an amide like the functional group. Amide is an N minus. Okay, that's all. Unfortunately, it's also called amide. So all you have to remember is lithium LDA is this structure, and you don't even have to really. So it has 2 isopropyl groups, and then instead of NH, it has a minus charge on here. Okay, and then the lithium is the counter ion. So that's it. So this is like T-butoxide. LDA is a sterically hindered base. So that's literally all you have to remember. You don't actually have to remember the structure. All you have to remember is LDA equals sterically hindered base, equivalent to T-butoxide. It's a stronger base than T-butoxide, so you can use it for really, really fancy reactions. Okay. So the LDA, we have a strong base. We have a secondary alkyl halide. What do you guys think happens? E2, right? Because we have a strong base, we have a pretty good leaving group, and that puts us in the position where we have E2. Okay, so we're going to have E2. Now LDA, where does it take the? Again, we have 2 beta hydrogens. Or several different beta hydrogens, right? On the methyl group and over here on the CH2 group. Which one do we take off? The methyl, because again, it just follows Hofmann's rule because it's sterically hindered, okay? So that means we form the Hofmann product. Okay, I'll draw you the arrow pushing. Right, LDA takes off, like before, LDA takes off the proton, kicks out the halide. We don't have to worry about E or Z in this case, because there is no E and Z, okay? Because there's 2 hydrogens attached here, so we don't need to worry about E and Z, okay? Good? Caroline.
Do you have to draw in the minor for this? Like the substituted?
Yeah, so ideally, if you want to do it really, really nicely, you do it like this. Major plus minor, okay? You do it like this. And then here you have E and Z. So, okay, so then hold on. Okay, so let's say if you now draw the minor product. You see now, I don't know if it's E or Z yet. Because for the minor one, let's go through this, okay? You see the minor one, I know you have 2 beta hydrogens, so it doesn't matter, okay? So will it form the E or the Z? The E, again, because of Zaitsev's rule, right? Because it has 2 beta hydrogens, it can form both the E and the Z, and in this case it forms the more stable E, okay? So the minor, you will write it like this. So the perfect thing to do on the exam is to write it like this. Major plus the other product minor. That's the absolute perfect solution. Yeah. All right, but if I'm not specifically asking for, if you just draw me the major and the major product is correct, and I'm asking you for the major product, that will give you all the credit you need. All right. If you draw both products, label the one which is major, label the one which is minor. All right. Does it make sense? Yes. Question.
Why is the second one the minor one?
Why is the second one the minor one? Because of Hoffman's rule. So we have a sterically hindered base. It will take off the proton from the less sterically hindered position, which is the methyl group, rather than the CH2 group. Okay? All right? So let's go to the next problem. Here. Missing products, substitution only. You need to figure out the mechanism. So it's substitution only, so it can be either SN1 or SN2, right? Those are the two options. Who thinks it's SN2? Who thinks it's SN1? So about half-half. I think it's SN1. Why? Because it's not a good nucleophile. This methanol, we said, it's not, but this, which is not, instead of saying not a good, it's just called a weak nucleophile. Weak nucleophile, okay? So it's a weak nucleophile, and because it's a weak nucleophile, it cannot directly attack, particularly not a secondary carbon, which is fairly sterically hindered already, okay? Remember, secondary alkyl halides are kind of in between. They can do both SN2 or SN1, all right? So that means if we have a bad nucleophile, so it's not going to attack, it's going to wait until the alkyl halide breaks. So the mechanism is we leave, the leaving group goes away, and now we form a flat thing, all right? We form a flat thing. Now look at this. Let's go for the major product. Okay, so the minor products are probably going to be this thing now, reacts with the chloride, right? And the chloride can come either from the top or from the bottom. So you can get, this gives minor products, which probably look like this. Where, one is the cis product, right? Where now sorry, not the chloride, the methanol, right? OCH3. So you form this thing, plus, okay, and then you deprotonate it. So I need to save some, so you know how to deprotonate this, right? You can draw the mechanism. So the final product here looks like this. But I think that's a minor product. Okay? Then the other thing which happens is you get another minor product where you can attack the carbocation from the bottom. The methanol comes in from the bottom, okay? So it looks like this. Now here it's pointing back. Now what else happens? Those are, I think, both minor products. What do you think happens with the major product? A hydride shift, because you see, this is secondary carbocation, so it shifts a hydride now to get to a tertiary carbocation. So which one shifts? This one. Shifts over, look. And what you get is you get a rearranged carbocation. This is a pretty hard question. Okay, which is flat now here, all right? You see that? And now the methanol attacks this carbocation like this, all right? And we're gonna get this product. So this, and then I'll write this shortly. Okay, I will say proton transfer. Of course, there's a proton transfer step here, right, before you get the final product, and then OCH3. Now, do I need to write plus enantiomer? Who thinks I need to write plus enantiomer or write the enantiomer? No, I don't have to because it's not chiral, okay? It's not a chiral center, so it don't have to worry about the enantiomer, all right? Done. I think that's the major product. That's a pretty hard question. It's a pretty hard question. Yes?
Even if it wasn't symmetrical, how could you make the enantiomer if the carbon that's coming out of the board is already there?
Oh no, it doesn't have to come out of the board. You see that the step which you see this part? Yeah. So here you see the carbon. So this thing is now flat. Okay? So if the methanol comes in from the bottom, you get the one which I drew there where the carbon is pointing to the top, right? Because the methanol comes in from the bottom. But remember, this part is pretty much, this carbocation there is flat, the green carbocation. So the methanol can come either from the top, in which case if it comes from the top, the carbon will point down and the methoxide is pointing up, right? So it can either come from the front or from the top or from the bottom. And then that's how you get both products, all right? But in this case, it doesn't matter because they're the same, right? Because there's no chirosine, all right? Let's move on. Provide missing products. What about here? So you basically eliminate twice. This you eliminate twice, and you get an alkyne. Okay? Done. Why? This I probably wouldn't put up, but it's similar to the lab. That's what you did in the lab, didn't you? Right? You eliminate once, and then you eliminate twice, like in the lab, all right? You guys good? Oh, that was too quick? Okay. Sorry, keep going. Question.
What does 2EQ stand for?
Oh, 2EQ, 2 equivalents. Okay, that's important. That means how many moles of a reagent you're adding. That matters, okay? If you just add one equivalent, you just get the alkene. If you add another equivalent, then there's more base there, so it takes off another proton. Okay? So this is equivalence. That's a great question. Pay attention to the equivalence, okay? Like, it depends how many moles with respect to the starting material, moles of starting material you add, okay? These are all pretty hard questions, okay? I'm not going to give you only questions like this, which are going to throw you off, okay? There might be a couple of them, but not only. Yes?
I have a question about the last one. So the reason why the hydride shift...
This one? Yeah.
Yeah. That's because since it's a two-step or more than one-step reaction, it has a chance to actually perform a hydride reaction?
Yes, it has a chance to perform a hydride shift because you formed the cation in the first place.
Yeah.
So if you did an SN2 reaction, you can't.
Yeah.
Because then you never formed a carbocation.
Okay.
Exactly. That's a very good point. So you see, the reaction mechanism, whether it's SN1 or SN2 or E1 or E2, is absolutely crucial in telling you what else can happen in the reaction. Okay? And about the stereochemistry. Okay? So that's the alkyne. What about this one? What about this one? No. Sorry. Yeah, let's see if you can figure it out, okay? This is a hard one. These are all hard ones, okay? I don't want to give you two easy ones not to practice. Otherwise, you're going to go home and feel like you can do it already, okay? And you stop practicing. So, what's happening here? This is a leaving group you have never seen before. It's not an alkyl halide. This is the leaving group. You see, it's a positive charge. That's basically ammonia is the leaving group, right? If you do something like this, ammonia will go away. That's a good, right? You should recognize this as that's pretty acidic, an ammonium, okay? So this is a leaving group. Does that make sense? So I will highlight this. This leaving group. Leaving group, okay? And you haven't seen it before. I'm aware of that. But that's my experience makes it hard. It requires some imagination. But you have to imagine what leaves the easiest, okay? It's like a protonated water. You have seen that. A protonated alcohol can leave. This is a protonated ammonia which can leave, okay? Now, can we do an elimination reaction? No, because if this is the leaving group, this is the alpha carbon, this is the beta carbon. On the beta carbon, there's only one beta carbon and there's no hydrogens attached. So you cannot have an elimination reaction. Most likely, unless you had like some sort of an E1 reaction and then, you would have you could have a hydride shift and then eliminate or something. But we're not going to do that. So then the thing is, look at the reagents, all right? It's a pretty good nucleophile, so it's probably going to be SN2, right? Because you can't have elimination. You have a good nucleophile, you have a good leaving group. Looks like a good leaving group, so it's going to be SN2, okay? SN2, and here the negative charge should be up here. So the negative charge, one of those lone pairs is going to attack, do an SN2 reaction, and then we're done with this, okay? Here we go. F, methyl, and then here we put, what are you forming? The OCH3, okay, directly. Because now here you're using the methoxide anion to attack. All right? Good? Shh. Okay, let's see. We have 10 minutes. I'll show you how the other ones go, okay? cut down your questions a bit. I mean, you can ask later, okay? Let's just go on, okay? Worst case, if we don't make it through all the problems, I'll just upload the answers, okay? All right, let's go to the next one. This one. These are pretty quick. What about the reagents? So again, you need to figure out SN1, SN2, E1, E2. What reagents do we have? Sodium azide, N3. N3 minus. Any guesses? Is it a base or is it a nucleophile? Nucleophile. It's a strong nucleophile. Did I give that to you in the table of reagents you should memorize? So what I'm going to do for the exam, okay, to help you a bit, is this table where we wrote down in lecture, the reagents like cyanide, SH minus, those kind of things. Those are the good nucleophiles, okay? And of course there's more than what I wrote down, so I'll try not to give you something unless I'm giving you the product or something. You know, I'm going to not give you some random nucleophile you've never seen before, okay? I'll try not to do that. So I'm going to give you something out of that table, all right? So this is N3 minus is like CN minus. It's a good nucleophile, okay? The way you can tell is because things are delocalized. Electrons are delocalized. So that means good nucleophile. And what about the substrate? Secondary, pretty good leaving group, right? It's a good leaving group, it's the chloride. Good leaving group. And secondary, alkyl halide, can do SN2 reaction, right? So that's what's going to happen, an SN2 reaction. And so then the SN2 reaction here proceeds with, here now it's inversion of the stereochemistry, right? So this methyl stays the same, and that's why the methyl is there, to test whether you see whether it's inverting the stereochemistry. And then the azide comes from the back. See, because you have backside attack in SN2 reactions. Okay, does it make sense? Okay.
It would only be in the SN1 that it's like do.
Yeah, and SN1 would change. It would not give you clean backside attack. It would give you both products, the cis and trans. But because you have a good nucleophile, it doesn't want to do SN1. It will just, azide is good enough of a nucleophile, so it directly displaces it. All right? Let's go on. All right? Oh, we have more stuff. Sodium hydroxide. This will just give you the Zaitsev product. Does it make sense? This will be an E2 reaction. Zaitsev product. So you get some Zaitsev product. You get some Zaitsev product, right? Because you have two hydrogens you can take off. And then plus, so this would probably be the major product. Plus the minor product would be the substitution product. Right? You can get SN2 substitution with hydroxide because it's a pretty good nucleophile as well. It can either act as a base or as a nucleophile. So in this case, then you get inversion of configuration. So if we put the alcohol here, I think the methyl has to point back. Okay? Does it make sense?
Did you get the Hoffman product on this too?
You would get a little bit, so this is probably minor, right? And then plus the Hoffman product. The Hoffman product would be also another minor product you can get. Which looks like this. Okay, let's go on. Let's see. Are you guys good? Sorry. You guys still want to draw something? Huh? Because you have two beta hydrogens, I think, yeah, you get a little bit of the Z, but it's not favored. In this case, you get the more favored one. The E product is favorable, so you get that one preferentially. Because we don't have to worry about the anti-periplanar in this case, because they are, you have two beta hydrogens. You can take off, both can rotate into the anti-periplanar conformation. All right? So, this one is kind of similar. So you get, here you don't get any substitution product, right? no substitution because substrate is tertiary. Okay, no SN2 product here. If you draw the SN2 product here, that's not great, because remember, you never get SN2 with a tertiary substrate. So now we're going to get elimination, and elimination can happen. Again, this is small base. So the major one would be the Zaitsev product, where you form the more stable alkene, the internal one, the more substituted one. So you're going to get this one as the major one, okay? All right? Like before. So now, you guys good? So I'm rushing through this. We put a lot of problems here. Similar here, T-butoxide. Now you don't make the Zaitsev product, you make the Hoffman product, right? So you deprotonate from one of these methyl groups, one of these hydrogens. Because those are, and not this one, because this gives you the more, this is too sterically hindered to be attacked by the sterically hindered base, okay? Again, so the major product here would be the Hoffman, this would be the Hoffman product, which looks like this. See that? All right. So, let's continue.
Did you have substitution?
Good question. No substitution because again it's tertiary. No substitution. No SN2. The only way you can get substitution to happen is in an SN1 process. But if you have a good base, the E2 process is much faster. Okay. So. Okay. Now this is the hard stuff, right? Really, this is the hardest thing. So this is the anti-periplanar thing. Okay. Because now you see you have. This I make on purpose. This is the alpha carbon, right? I'm telling you it's an E2 reaction. And you see the E2, basically, you see this is the beta carbon, as it already says, okay? And there's one hydrogen only, okay? So only one H on the beta carbon, right? So that means we have to rotate anti-periplanar. Here we have to do this rotation. So I'll show you an easy way to do it. Okay? You look at this carbon-chlorine bond. I went through this in the review session. You can rotate all of the bonds and make them into the plane. That helps. The other thing you might want to do is just literally get a model, bring your modeling kit, build the molecule, look at it, rotate the bonds anti-periplanar, like the carbon-chlorine and the carbon-hydrogen you're going to deprotonate. Rotate it anti-periplanar. See if it's going to be cis or trans. You're done. Okay, with the model, it's really easy. So I'm just showing you if you forget your modeling kit, that's the backup, okay? So here's how you do it. You see this carbon-chlorine bond down here is coming forward toward you, okay? Which one of the bonds here on this carbon is anti-periplanar to this bond right now? This one. You guys see that? If you draw a Newman projection, you see they're anti-periplanar to each other. You guys see that? So here's the trick. Okay, I think that's actually easier than doing anything else. Is you basically, you leave the whole left part of the molecule here. This all stays the same. You don't touch it. Okay? We just redraw it. All right? All you have to do is correctly redraw it. Nothing else. You just redraw that part of the molecule. Then you go here. All right? Now, what we're going to do is we're going to rotate around this bond here. This fat bond here. You can see that? Let me make it like yellow or something. This bond. We're going to rotate around this bond. And we're going to rotate it such that this hydrogen ends up where the carbon is. So if we do that, we basically move the hydrogen to the position of the carbon to the position of this ethyl group, and the ethyl group to the position of the hydrogen. You guys see that? That's how we just permute the substituents. We rotate it around. Okay? So, basically that means the hydrogen will end up here. The carbon or the ethyl group will end up over here. And the carbon will end up here. You guys see that? And now you eliminate. See, now they are anti-periplanar. So it helps to draw in the additional hydrogen here. Right? So they are anti-periplanar. You eliminate. you see what happens is the methyl, this T-butyl and the methyl here, they are on opposite sides. And the, oh sorry, this should be an ethyl group, okay? I drew too much. This should be an ethyl group. And the ethyl and the hydrogen, they are on opposite sides. You guys see that? That means you're going to form, so you're going to do E2, and now you form the thing where the T-butyl, the olefin, where the T-butyl and the methyl, they're on opposite sides, and the hydrogen and the, hold on, yeah, the hydrogen and the ethyl are on opposite sides, right? You guys see that? So is this the E or the Z product? This is the E product. That's the only thing which forms. Does that make sense? So that's the anti-periplanar stuff. Okay? So let me quickly, give me maybe 2 or 3 more minutes. I'll run you through the rest of the problems. Okay? Does that make sense? If you guys have to leave, that's fine. I'll upload the video so you can watch it online after. Question? Yeah. Oh, the Z. Absolutely. I'm absolutely wrong. They're on the same side, okay? That means Z. German should be my native language, but I'm slowly forgetting it, okay? That's fine. That's fine. That's the Z product, all right? Let's move on. Same deal here for the following substrates, right? What you do is you rotate it. So you see, you could, this is the hydrogen. Well, this is a trick question, okay? So if I'm giving you T-butoxide, it will just, let's simplify the question, okay? If I'm giving you T-butoxide, it's going to just form this less sterically hindered olefin. Done. All right? If I'm giving you a small base, then you have to take off the proton from here, and then you can think about what's the product. All right? Like before. All right? So let's say it's with T-butoxide. That simplifies the question. Let's go to the next one, okay? Because I want to get you out of here before it's noon. So this is another important case. Whenever you have a ring, and a cyclohexane ring, and I'm asking you to do an elimination, or it could be an elimination, you have to draw the chair, okay? So you do exactly what we have done before. When you draw the chair, you just draw the chair, okay? And remember, where does the bromine have to point? It has to be axial, that's the rule, right? So the bromine has to be axial, it's obviously pointing up. So we put it, for example, in this axial position here, and then the methyl is pointing where? Down, so it must be axial here, okay? Now look at this. This is why you have to do it. So here is a hydrogen, this is a beta carbon, right? So this is one of the hydrogens. The other hydrogens are here. One is here, one is here. Which one is anti-periplanar to the carbon-bromine bond? The one down here. That's the only one. None of the others are. That means that's the only one you can take off, regardless of if you have a big base or a small base or whatever. So you're taking it off. You take the base, okay? You take that one off. You can only take off the one which is anti-periplanar. That's important, right? That's why we had to draw the chair. And so that gives you the product. Essentially, we took off one of these hydrogens here, all right? So that gives you the product which looks like this, where the methyl is still down, and you have a double bond over here. So the tricky part will be, let's say I'm going to give you something like methoxide, which is a small base, right? And if you don't draw the chair, you'll think it's going to take off the proton from the, to give you the Zaitsev product. But it can't, because it's impossible, because that proton is not anti-periplane. All right? Let's see what else we have had here. This was the challenge question, last one, okay? Then you are relieved. What happens here? What do you guys think? This is now an intramolecular SN2 reaction. So sometimes these reactions can happen within the same molecule. Okay? So here you see the sodium hydroxide is a strong base. What will it do? It will deprotonate the strongest acid. What's the strongest acid in the molecule? It's not like, the CH bonds over here. Those are not very acidic, right? Not very acidic. What's the most acidic stuff? Is the alcohol. Okay, so it will deprotonate the alcohol. So I'm going to draw it like this. I'm going to draw it out. Okay, just one more sec. This will be quick. Once we do this, we take off to show the deprotonation. Right, you have to pretty much draw it like this. So the hydroxide is just acting as a base, deprotonating the alcohol, and so you form what you form is this thing, O minus Br. 4 carbons, right? Make sure you don't lose any carbons. Now what happens? Now it does an intramolecular SN2 reaction, all right? Like this. And what do you form? You form a beautiful 5-membered ring. I don't know if you find it beautiful. All right? So, that's it. I think that's all the problems I wanted to discuss. So what you need to do is practice this stuff. Keep practicing, okay? It's not that bad. Many of the things like Zaitsev, Hoffman rule, those things are pretty easy, okay? SN2 inversion of configuration, pretty easy. The hardest stuff is the eliminations where you have to rotate the anti-planar. If you follow this trick I just showed you, that's pretty easy, okay?